Our next speaker is Dan Carney.
Okay. All right. So I really appreciate everybody who's still in this room. It's late on a Sunday. I'll be quick, and I'm not going to talk much about technical stuff. I didn't think anybody would want to hear about technical work of mine at 12 o'clock on a Sunday. So I thought instead I'll talk a little bit more about Steve and what I thought certainly what he's done in my life. And I'll mention one technical output of that. And then I want to talk about something kind of exciting that a few people have heard about, a project related to Steve. So this is a picture of my defense, which, okay, there's lots of comments we can make on this. Anyway, it's a great memory, obviously. Especially since there's a lot of students here, Steve was around and quite active the whole time I was here, 2007 to 14, and sort of, I think, so Willie Fischler and Sonia Pabon were my technical advisors, but I TA'd for Steve for a couple of years and we had a lot of interactions. And I think he really had a very serious impact on how I think about physics. And this is sort of my attempt to synthesize what I got from him. So this has been discussed earlier, but I think Steve is just incredible he would always start from scratch and work his way through. And he made a lot of his living based on finding gaps in what was until then a standard story and then making it the standard story. This is something, I think this was published in some article once, but he told me this when I was young. He said, you should try to work on a topic where there's maximal confusion. Don't work on something that's been formulated and is precise. Find something where no one knows what the hell is going on. In particular, there was some anecdote where his friend told him that he was going to work on general relativity because it's a beautiful mathematical theory, and Steve decided that that was exactly the wrong conclusion because if you already have the theory, why are you going to work on it? So, of course, they connected to experiment. That needs no explanation. And then this is a kind of a sort of a joke, but when I came into grad school, it was the heyday of string theory again, and Ed Witten was the best guy on the planet, and it was like tempting to want to be Ed Witten. And then I tried that and I was like, I am hosed. That is not going to work out because I just don't have this sort of deep, spontaneous, creative insight all the time. And not to say that Steve didn't have that, but it was clear that Steve's style was more like he would, be a tank. He would just slowly move through a subject. And it really sort of personally enabled me to try to think, okay, maybe I could do physics in that fashion. So everybody talks about field theory, but I think a known but less appreciated aspect of Steve's work was he actually thought about quantum foundations and took it very seriously, and in particular tried to make it sort of real. So Steve did not sit around talking about philosophy of quantum mechanics. What he did was he would try to break quantum mechanics quite often. So this is a very beautiful old idea, precision test of quantum mechanics. So the idea was take the Schrodinger equation and make it nonlinear. And just see, how could we make an experiment that would bound this deviation from standard quantum mechanics? And this led to some series of experiments that people are still doing. When I was here, Steve was working on modifications of the Schrodinger equation where you would insert stochastic terms that would collapse the wave function. This was supposed to solve the measurement problem. So, he was doing this for many decades. Steve also thought a lot about infrared quantum gravity. I think he thought about quantum gravity at all scales, but he has a lot of famous results in infrared quantum gravity. And this is one of my favorite papers Steve ever wrote. So this is a paper which has a little theorem which says, suppose I have an S matrix. The S matrix has a massless spin 1 or a massless spin 2. Sorry, that is not massless spin half. That's spin 1/2. Asymptotic states. Then from these assumptions lead you to derive the Maxwell equations or the Einstein equations, specifically in the sense that you can show that you can generate the S matrix elements by field operators that satisfy these equations viewed as Heisenberg equations. So you really sort of can say, like, just from this asymptotic information, I can derive that there's some quantized field in the picture. So this is the only technical thing. There's just 2 slides on this, just to put those 2 pieces together in a funny way. So this is a paper I wrote during the pandemic. It's my only, well, I have 2 now, but this is my first single author paper. And I did it because I was totally alone. And I had the great experience of sitting there for 6 months reading these two papers I just showed you and thinking a lot about them. So I dedicated it to Steve. He passed, while I was writing this. Unfortunately, PhysRev are jerks and they won't let you actually dedicate a paper. So they removed the dedication in the published version and told me afterward. Never was happy about that. But anyway, no one cares. It's the published version. So on the archive, it still says dedicated to Steve. So just to say what this paper was, it's basically just a reverse engineering of some of Steve's work. So let me motivate why I wrote it, and then I'll show you what it says. So the motivation is, this is some line of stuff I'm deeply involved in. I hope Steve would have liked this line of thinking, but there's an idea that you can do an experiment that would probe these following questions. So what you'd like to do is ask, can the gravitational field be put into a quantum superposition? And then can I measure that? And then what I want to talk about here really quickly is if I did this, what would it mean? So the cartoon of this would be, here I have some massive object that sources a gravitational field. And what you like to do is say put that mass in a superposition of two different spatial locations. And so your naive expectation from quantum field theory would be that the gravitational field comes along for the ride. The gravitational field is now quantum superposed. And then you would want to measure this. So for example, by having a test mass gravitate to this. This is a challenging experimental proposal, but it's probably going to get done within a couple decades. This is a picture of a device where these people in Vienna are very seriously pursuing doing this kind of a thing. I got involved in this many years ago now, and a lot of what I've attempted to do is at least channel Steve's philosophy. I would never claim to be anywhere near the skill, of trying to be precise about, suppose you did this, like what does this actually tell you? And so maybe I'll skip the proof, but I wrote this is this paper I just showed you. You can take that old graviton paper of Steve and just reverse the logic and prove the following thing. Suppose I have a model where scattering there's an S matrix that's unitary, it's Lorentz invariant, and in which it's generated in the non-relativistic limit by a 1/r potential interaction. Then you can just take these assumptions, take Steve's argument, run it backwards, and prove that the asymptotic states have to have a massless boson that couples to matter with the right G Newton and mass coefficient. So in other words, you can basically prove that something like a graviton has to exist in the asymptotic state. It doesn't actually pin the spin, so it could be a spin 0 or 1 particle. Anyway, it's a simple optical theorem argument, and it really is just Steve's paper written backwards. And okay, why are we doing this? Because this is supposed to be trying to make precise what exactly you're looking at in these experiments. In particular, you're really testing, is the gravitational interaction generating a unitary dynamics, and does it have an entangling interaction? Yeah, okay. I think I'll skip the proof, but if people want to see it, maybe I'll write this. This is sort of how the proof looks. So what you wind up doing is writing some diagram that describes one of these experiments and show that, okay, well, there's some optical theorems, so I have to be able to cut a diagram and write final states that correspond to the interaction vertex that I'm probed in the experiment. All right, so much more interesting, I think, for this crowd. Here's my secret Steve project. So in 2010, Steve taught this course that was called Topics in Quantum Field Theory. A bunch of us took it. So I saved my notes from this course, and Joel saved his, and probably some other people have a copy. And I've just been sitting on them for a decade and a half. These were distributed to us as printed tech typeset documents with chapters numbered 33 through 37, which is indicative. They're full of typical, terrible Steve diagrams. And they're full of indices and all the usual stuff. So it looks just like, QFT volumes. So finally, last year, I thought maybe I should do something with this. And so I talked to Joel, and Joel and I talked to Louise, Steve's wife, and she said, you should publish those. She really was strongly requesting that we get them out into the light of day. She gave us the rights. We went and visited her. So this was a really sweet moment where we took a picture and she insisted that Steve be in the picture. So we have this stuff laying around and we're trying to figure out what to do with it. And we've been working slowly, but Joel and I are both junior faculty and totally overwhelmed. So it's taking a little time. We went on that same trip to when we met Luis, we went to the Ransom Center where Steve's archives are. And we found a bunch of cool stuff in there. One thing, I don't know if this is too small to read, but this is, can I zoom in on this? I can't zoom, sorry. This is correspondence with Cambridge University Press and his editor there. And what it basically says is something like, Dear Simon, I'm teaching this course. The notes are in good shape, but they're a little thin. I want to make them into volume 4, but there's not enough, blah, blah, blah. Okay, so it pretty much states that the idea here was that these notes were gonna become a QFT 4. So we talked to Cambridge University Press, and I think we think, and we sent a proposal of this out to a few people. There's just not enough to publish this as a volume 4, and I would feel very nervous doing anything like that posthumously. So the publisher kind of suggested to publish these as sort of lecture notes, like Steve's unfinished lecture notes or something. That's one option. Another more minimal option would be to just put them on the archive, and I think that would be a totally reasonable thing to do. But sort of the tentative plan is to go with this. So what's in the notes? There's 5.5 chapters, I'd say. So there's a chapter on thermal field theory. This is a slide of it. So there's all this stuff, partition functions, diagrams, there's all the resummation of Matsubara frequencies and all that stuff. There's, it builds up to Steve's old result about restoring symmetries by turning temperatures up. There's a really wonderful chapter. This is the one I know the best. I've used it for many years. There's notes on the in formalism and how you calculate cosmological correlators. There's a chapter on the heavy quark approximations. This is something I know very little about. Although I remember solving these problems, and it was not my, okay, the limits of my field theory skill for sure. There's a chapter on QCD at large N. This is pretty cool looking. There's a chapter on CFT. This is like a really beautiful old school way of thinking about CFT. I mean, he really just goes through the symmetry rules, and it's kind of like the beginning of Ginsburg's notes if you've read those. But there's a bunch of stuff. There's also a chapter on ADS CFT, which is, I think, of historical interest, but not much pedagogical interest. It's pretty bare bones. And so that's what's in there. So I wanted to do, Joel and I were trying to do this ourselves, but I think I wanted to just put this out there now because this has been going on for some months. We really would like to, we told Luis we would get these out there. So we'd like to fulfill our commitment to her specifically. I think it's also of interest to the community to see these. So our goal has been to do something pretty minimal. So we'd like to just clean up the notes. We have them typeset in tech, but there's pieces, there's little bits missing, there's some typos, things like that. So the idea would be to clean them up with very minimal intervention, just to make sure they're consistent and complete, self-complete at least. And then publish them with Steve as the author, of course. So if it was published and made any money, which I doubt it would make a ton of money, but any proceeds, we don't want them, obviously. The thing I wanted to say here in public is that we are not me and Joel are not domain experts in a lot of this stuff. And we really have the need for domain experts who are willing to spend real time looking at this material and editing it in this way. So Joel and I can handle the in chapter, but the heavy quark, the large N, the CFT, and the thermal field theory chapters, okay, we would really like one person each, roughly speaking, to volunteer and do these. And of course, what we're looking for is people who are really experts in these topics, and they're comfortable with Steve's notation, style. They're not going to want to rewrite anything. So let me just put that out there. If you are interested in this, or somebody who you think would be good for one of those topics, this is my email, or you can just find me. Okay, so that's it. So in the meantime, though, I wanted to say, big thanks to Katie and everybody else who put on this conference. It was really fun. I wanted to say there's a very famous story. Maybe people have heard this about Steve taking over Schwinger's office in Harvard, but I thought this was an appropriate Steve story. So if you haven't heard it, Steve apparently was given Schwinger's office when he got his professorship in Harvard. And the legend, I don't know if this is true, is that Schwinger had left his shoes in the office. And the implication being you have to now fill Schwinger's shoes. So I hope we can do the same thing in Austin moving forward. Thanks.
Thanks, Dan. Question, comments, volunteers?
Well, think about it.
Yeah.
And truly, for to make it clear, I really would appreciate suggestions for names. So in particular, like thermal field theory, I don't know who's an expert on this. Could ask Alan. Okay, I'll think about that. Right. Yeah, we need able, willing people. So, okay. Anyway, if you think of somebody, I'm pleased just get in touch.
Thank you, Dan.
Cool.
Thanks, Dan.